Hello. We're going to take advantage of the combustion test step to learn about combustion, how software can help us understand chemical reaction. Okay, so we'll solve these simple problems, how to balance a fuel and oxidizer reaction, how to find air-fuel ratio, and things of that nature. We'll not limit ourselves only to these particular questions. So let's get started. So we'll follow an open system, open combustion chamber in which there is flow of fuel and flow of oxidizer, which could be air or pure oxygen or any combination of oxygen and nitrogen, are entering. So obviously you follow the open path and a specific, steady, specific path, and come to combustion and chemical equilibrium. Once you click there are several options. The non-premixed combustion means fuel and oxidizer are coming separately to combustion chamber, as opposed to pre-mixed combustion. For instance, there are many examples where fuel and oxidizer are mixed already and sent for burning. And finally, on this branch, we'll handle something called chemical equilibrium analysis, where you don't know what is produced as a result of chemical reaction, and using thermodynamic analysis to figure out what is in the combustion product. So this is the most advanced part of combustion. It's covered in chapter 14 in your book, and these are covered in chapter 13. Okay, so let's start with the basic non-premixed combustion. Means fuel and oxidizer, they're entering a combustion chamber through separate inlets. And we can use either the PG model or IG model. That's how, constant specific heat assumption. They look identical, except IG model will produce a little bit better results if you do an energy analysis, more accurate result. Okay, so here I launched by clicking the HTML5 button, and it looks a fairly complex setup here to analyze combustion. But once you get the hang of it, you'll find very simple. First thing first. This is the composition panel where we set up the reaction. State panel where you find properties of the mixture. It could be a fuel, oxidizer, or products. And the standard graphics panel where you can see the states on a graph. And I/O panel when we can write a small program to solve more complex problems. Okay, so let's start with the most simple, the most basic reactions. Let's say hydrogen is burning with oxygen. So here we're already in the fuel panel. First, a little bit about the composition panel. You see there is here, you can see fuel, oxidizer, and products. You can hear how we set up our reaction. Sort mixture button basically means all these are alphabetically sorted if there is too many of species. It's the initialization button, and then there is a lot of action we can select. We'll come back there. You select an action and click the execute button to perform the action. On the left hand side are the fuels that are available. In this case, fuel. If you go to oxidizer, these are the oxidizer that we have available. See, you cannot go to the product right now because we haven't selected fuel or oxidizer. So instead of giving a random list of components for products, this TESTapp is smart. It recognizes what fuel and oxidizer you pick, and based on that, it gives you only those products that are possible, atomically possible. You cannot have carbon, hydrogen, and oxygen in the reactants and somehow have nitrogen in the products. Atom cannot be created in a chemical reaction, which is simply rearrangement of atoms. What else we need to know? Keep an eye on the help panel. It gives you tips every step what to do next. Okay, so let's start. To select a fuel, all you have to do is to click anywhere on this row, and by default it says 1 kilomole. Of course, you could select different ways of this, how the fuel is described. It could be by kilomole or kg or pounds or percent by mass, or mole, etc. We'll just stick with kilomole. Let's say we have one kilomole of hydrogen. We have to click the add button, then only is added to the fuel. If you want to remove it, if you made a mistake, click again and click the remove button. That goes away. So that's quite simple. So notice that as soon as we selected hydrogen, it produces a little pie chart. If sometimes it could be a mixture, that becomes very helpful, that chart. So we are done with the fuel. Well, even before we select oxygen or oxidizer or products, let's look at the action. There are a lot of things you can do almost automatically, because as soon as you know your fuel, there are some things you can do immediately. Well, notice that as soon as we selected fuel, it told us something about the mixture. It says that mass added is 2 kg, mole added is 1 kilomole, which are all this here, and mixture molar mass. In this case, mixture is a pure hydrogen. And essentially, it summarizes about the entire mixture. Of course, these numbers will match because we have just one component in our mixture. So, air-fuel ratio and air-fuel ratio on the molar basis, question mark means we still don't know that yet. It depends on what kind of reaction we want. Suppose we want a theoretical combustion reaction with pure oxygen. That means hydrogen is burning with pure oxygen. Theoretical, recall, means reaction is complete, only H2O will be produced, and there will be no excess hydrogen or oxygen left. So you just click this button and execute. I mean, you select that option and execute, and here we go. If you come down, you'll see your reaction is balanced, and the tick mark means the reaction is balanced. 1 kilomole of hydrogen reacts with half a kilomole of oxygen, producing H2O, 1 kilomole of H2O. And of course, the air-fuel ratio on the mass basis, or the mole basis, is 0.5. By air-fuel, we mean oxidizer fuel. Air-fuel is a standard terminology, but in this case, the oxidizer is pure oxygen, so it really should be oxygen-fuel ratio, 0.5, but on mass basis, 7.94. You need 7.94 kg of oxygen to burn 1 kg of hydrogen. What else do you know just by balancing the reaction? We can go to the oxidizer panel, take a look, and we figure out, we can see how the pure oxygen is shown here, and we can go to the products panel, which shows that product is only H2O, nothing much. Okay, let's set up the reaction with theoretical air instead of theoretical combustion with pure oxygen. Air means, okay, let's execute and take a look at the reaction now. Look, the air means there is oxygen and nitrogen at a certain ratio. 1 kilomole of oxygen carries 3.76 kilomole of nitrogen, if you recall. The reaction is against balance through an atom balance. There is some excess nitrogen left because nitrogen never participates in a theoretical reaction. And because it's theoretical, notice that H goes to H2O only, and there is no oxygen left or hydrogen left. There is only perfect amount. If you go to the oxidizer panel, you can see how air is composed. Air is composed of, as you can understand, 23 point. This is the mass fraction. This is the mole fraction of oxygen and nitrogen, and this diagram is only for mole fraction of air. You can put your pointer over, and that gives you a little more information of each species, each component of the mixture. And of course, the products will have nitrogen, excess nitrogen, and H2O. So we have done with theoretical reaction. Then again, the air-fuel ratio is given here. If you come back to, it's shown here, air-fuel ratio. And because the reaction is theoretical, then the actual air-fuel ratio and theoretical air-fuel ratio are same, and that's shown in the oxidizer panel. And in the products panel over here, you'll see it will make sure that your products have all the atoms that is supplied by the reactants. All right. Let's super initialize and start over again. This time, let's say we are burning methane. And we already know theoretical reaction, theoretical combustion. Let's do a theoretical combustion with air. And again, you'll see that how methane reaction is balanced. You should be knowing how to do that manually just by, taking care of each atom on both sides. All the unknown can be found there. Again, the air-fuel ratio is shown here. Notice this is called theoretical air-fuel ratio because the reaction is theoretical. But suppose we set up a reaction which is not theoretical. Suppose we have a little bit of excess air. So let's say the methane is reacting with complete combustion with known excess deficient air. So we go to option 2B. We know it's complete combustion means carbon will go to CO2, H will go to H2O, and known amount of excess air. How do you specify that in the known amount? Lambda. Lambda is percent theoretical amount. In other words, when lambda equals 1, lambda equals 100%, we have exactly theoretical amount. Suppose we have 20% excess air. Then you say lambda is 120. In that case, when you click the execute button, again the reaction is balanced, as you can see. Methane reacts with, this is the air, oxygen and nitrogen mixture, producing complete combustion, H2O and CO2. There is no CO or anything, and some leftover air here, some leftover oxygen because we put excess air. So the reaction is balanced again, but the theoretical air-fuel ratio doesn't change, right? Theoretical means there is no excess air. So notice, to burn 1 kg of methane, we need 17.1 kg of air. But if you go to the oxidizer panel, it will tell you the actual air used. We are using 20% excess, so you can find the air-fuel ratio will be higher. This is the actual air-fuel ratio, 20.5, as opposed to, their ratio, actual air-fuel ratio and theoretical air-fuel ratio is called percent theoretical air, or lambda. Let's go to the products panel, and you can see that the composition is shown again in a pie chart, and vast majority of it is nitrogen, but you can figure out the mole fraction of each from the chemical reaction right here, right? If you know every mole of every species, so you know the total mole of the products. So for instance, what will be the mole fraction of the carbon dioxide? It will be 1 divided by 2 plus 1 plus 9.02 plus 0.4. You'll find that will be the carbon dioxide mole fraction, 0.08. Okay, let's make it a little more. Let's explore some other features. Suppose we have a deficient air. So suppose methane reacts with this time again known excess deficient air. Suppose we say it's reacting with 5% deficient air, which means 95% theoretical air is used. What will happen now? As you can imagine, if there is less oxygen than we need, some methane will be left over after the reaction. As you can see, this reaction, some methane is left over. All the oxygen is consumed. Of course, nitrogen will be exactly identical on the reactants and product side, because nitrogen doesn't participate in a theoretical reaction, in a complete reaction. Okay, what other features do you want to illustrate? Okay, let's suppose we have a mixture of methane and hydrogen, and we know what is the oxidizer also. It's not one of those standard stuff. So let's try. Suppose we have 1 kilomole of methane, we add, and 2 kilomoles of hydrogen. So we enter 2 here. So we have a fuel mixture now. So it's a little more complicated. So notice the reaction gets updated. Here's the fuel mixture. We don't know the oxidizer. We don't know the products yet. We could select one of those standard things, but no, we want to know, this time we know what the oxidizer is. Suppose it's given that oxygen is 5 kilomole of oxygen and 5 kilomoles of nitrogen are flowing into the combustion chamber, let's say every second. So we have the fuel mixture flowing in, we have the oxidizer mixture flowing in, and we know their compositions. So how do I balance this reaction now? All you have to do is that we know the fuel and we know the oxidizer, and then we can go and find the appropriate action to take. So look at 2D, complete combustion with user specified oxidizer. So if you click there, we get complete combustion and we execute, and as a result the reaction is balanced for the given amount of oxidizer and fuel. As you can see, this is the oxidizer panel, so air fuel actual is 14.9 in this case, and air fuel theoretical is 8.97. So therefore, in this particular reaction that we set up, what is the percent theoretical air used? Lambda is 167, so 67% excess air, not air, oxidizer has been used in this reaction. So go ahead, play with this so that you understand how to set up a reaction using this, and we'll talk about energy analysis in a separate video.